In section 8.3, we're going to be looking at trigonometric integrals. Trigonometric integrals is a technique that we use when we're working with integrals that involve sines and cosines, and also secants and tangents, and some other trig combinations as well. The two that we're going to be focusing on are the ones that involve sines and cosines, and the ones that involve secants and tangents. When we're working with integrals that involve a mix of sines and cosines, we could be looking at something as simple as the integral of sine x cosine of x, which we don't really need any other integration techniques other than our u substitution from Calc 1. So we're not going to need any tricks for these types of integrals. Another one would be something like sine squared x cosine of x. This is a nice little u squared du, and I don't need any tricks or tips for this as well. But what if we had something like sine to the 5th x cosine to the 4th x dx? Here, our nice little u substitution will not work. So here I'm going to use some other techniques. And basically, you need to know the techniques for combinations of sines and cosines. The other combinations that we're going to be looking at is integrals involving a mix of tangents and secants. Now these could be some Calc 1 type problems too. For instance, if I had the integral of tangent of x times secant squared of x, this is a nice little u du as well because the derivative of tangent is secant squared. However, what if we had something like tangent to the 4th x secant cubed of x dx? You know, is there a way I can integrate this, and can I use the process of trig integrals for this? These types, where it's a nice little u sub in some fashion, I would expect that you'd be able to do these type, because again that's more of a Calc 1 problem, just a nice little u sub problem. These types, when we're looking with trigonometric integrals where the nice little u substitution will not work, I would say be able to look the process up. I wouldn't memorize this process, but be able to know where they are at in your text so you can follow the directions. So again, up here, for integrals of sines and cosines, make sure you know the techniques. Those come up often. Down here when we have integrals of tangents and secants, know that, gosh, there's a process that's associated with this. I need to go look it up in my text and see what it is, unless it's a nice little u substitution type problem. If it's a nice little u substitution type problem, you should be able to figure out exactly what's going on in terms of a Calc 1 problem. Now in order to work these problems, there's some identities and some other trig information that we're going to need to know. The first one that we're going to be looking at is the good old Pythagorean's theorem. Sine squared of x plus cosine squared of x equals 1. Now the Pythagorean theorem works for any argument, not just x here. This could be 3x as long as the argument is 3x over here as well for the cosine squared. So the Pythagorean identity is one that we're going to be using as well. Some other identities that we're going to be using are called the half-angle identities. Now we're going to be using these identities to rewrite integrands in order to get them to a spot where we can actually integrate them. The first half-angle identity is sine squared of x is equal to 1 minus the cosine of 2x, and please put arguments in parentheses all over 2. The second half-angle identity is to rewrite cosine squared of x as 1 plus cosine of 2x all over 2. So we're going to be using these identities as well. A couple other ones that come in handy. They're not half-angle identities, they're just some other trig identities that are nice. The sine of 2 times an angle, the sine of 2x is equal to 2 sine x times cosine x. And one more is the cosine of 2x. And there's actually a lot of identities associated with the cosine of 2x. They're all in the back of your textbook in the back cover. Cosine of 2x is equal to cosine squared of x minus sine squared of x. So a lot of trig review here. Now, you want to make sure that you have this one memorized. Okay, the rest of these will be provided. So here, this block will be provided for a test or a quiz. So Pythagorean's theorem, we've certainly memorized that one because we've used it so often, so that shouldn't be too bad. And again, the other ones will be provided. I would really put these on a note card so they're accessible to you because we're going to be using them often. The first example that I would like to look at is one that kind of shows that we don't really need any fancy techniques just because the sine and cosine are involved. So for instance, we could have sine cubed of x cosine of x dx. So just because you see combinations of sines and cosines, don't think that you have to apply some of these techniques. Sometimes a nice little u substitution will work. So the first thing you should always try with any integrand is a u substitution. So here, let's try the u substitution of u as sine of x. Du then, of course, is a nice cosine of x dx. And so when I rewrite this, what ends up happening is I have a nice little u cubed du, which of course integrates into u to the fourth over 4. Substituting back in for u is sine, so I have sine to the fourth of x over 4 plus c. So not all trig integrals involving sines and cosines or secants and tangents require the use of a particular process or algorithm to solve. A lot of times it's a u substitution that will work, and I encourage you to always try a u substitution first. For this first example that we're going to be looking at problems of the type where the power of sine is odd and the power of sine is not only odd but it's positive. Now this doesn't say anything about a cosine, so what we're assuming here is the first thing we look at is the power of sine is odd and positive. So for this example, when we have this occurring, what we do is we save out a sine. Okay, so that means I'm going to have a sine saved out, then I'll have a sine to an even power. We're going to convert those rest to cosines, that sine to the even power, using a Pythagorean identity, and then we're going to expand, distribute through the cosine if we have one, and integrate. So let's go ahead and look at an example that will fit here. Let's look at sine cubed cosine squared of x dx. So if we note here, the power of sine is odd, it's 3. 3 is positive, so we're set to go. We didn't really say anything else about this problem in terms of cosine. Well, the rule is that we should save one sine and convert the rest to cosines. So let's go ahead and try that. If we save one sine out, what's going to happen is that sine that we save out over here will eventually end up being my du, or part of my du. So this is just a rewrite of the exact same problem. So I've taken this sine squared and broke it up, or sorry, this sine cubed and broke it into sine squared times sine. Now the second step is to convert the rest to cosine. So this is basically our first step that we looked at here. We saved one sine. And eventually that's going to be our du. The second step is we're going to convert the rest to cosine. So what we're going to do is take this sine squared x and convert it to a cosine. Okay, and then everything else I just drag along. Now how would we convert sine squared of x to cosine? Well, usually what you're going to do here is to convert the rest to cosine using a Pythagorean identity. So again, we're going to convert the rest to cosine using a Pythagorean identity, and the Pythagorean identity that we like is cosine squared of x plus sine squared of x equals 1. Now you might think, well, what about these other half-angle identities you showed us? Well, the half-angle identities up here aren't going to work, because what ends up happening right here is our argument of our trig function changes. Here it's an x, here it's a 2x, and I cannot combine x's and 2x's in my arguments if they're going to be u/du's of each other. So this is a conversion, you're correct. Both of these are conversions, but they're not conversions that will work for this type of problem. Okay, so let's convert this. Now, if I use my Pythagorean identity, cosine squared plus sine squared equals 1. Sine squared is equal to 1 minus cosine squared of x. So there's my conversion. And again, this is a direct substitution. So that was step 2. So step 1, save one sine. Step 2, convert the rest to cosine. The third step is to expand, and then of course then we'll integrate. So let's go ahead and look at that third step. In my third step, when I expand this, I'm going to distribute this entire cosine squared sine x dx factor through the binomial. So I'm going to distribute this through. So I end up with cosine squared of x sine of x dx, okay, minus cosine to the fourth of x sine of x dx. And what I'm going to do is rewrite both of these as separate integrands. So that was step 3. So step 3 was to expand, meaning distribute through, and then our fourth step will be to actually integrate. Now the integration here will be a two-step process because I have two different integrands, although the u substitutions that we're going to be using are the same. So here I'm going to let u equal cosine of x. Du then it would be negative sine of x dx. And that's going to work for both of these. U is cosine of x, du is negative sine of x dx. So, rewriting, make a little bit more room here, rewriting this, we end up with a u squared, but I don't quite have my du. I need to multiply by a negative on the inside, compensate with a negative on the outside in order for my du to work. So I have negative u squared du for my first one. Now for my second one, the same thing. I need a negative on the inside, compensate with a negative on the outside. So here I'll have plus u to the fourth du. And of course, integrating from here is going to be pretty easy using your good old power rule. But the rule I'm following here is my integration step, so this is where I integrate. So integrating, I end up with negative u cubed over 3 plus u to the fifth over 5. But of course this is not my solution because my original was a trig function in terms of x, and so should my solution be. So for here, I end up with a negative, u was cosine, so negative cosine cubed of x over 3 plus cosine to the fifth of x over 5 plus c. And I really recommend you finding common denominators and whatnot here. The reason we'll want to do that is eventually we'll be evaluating these, and they're easier to evaluate when they're simplified. So common denominator would be 15, so I have a minus 5 cosine cubed of x plus 3 cosine to the fifth of x all over 15. Of course, dragging along my constant of integration. And then it looks like, in terms of simplification, I could pull out a cosine cubed and a 15th. And if I do that, I'm left with 3 cosine squared of x minus 5 plus c. Now if you check these in Maple, a lot of times what Maple will do is it'll take this cosine squared right here, and it will use a Pythagorean identity that cosine squared is equal to 1 minus sine squared, and distribute and combine some like terms. So you might not see an identical solution, but algebraically they're probably similar. And one way to check is to go ahead and graph both of them in Maple, your solution and Maple's solution, and see if they match, see if they're the same type of graph. So this is my solution.